Hello learners, today we are going to solve some important numerical problems related to operational amplifiers. So, my name is Dr. Subhas Das. I am working as the Associate Professor in the Department of Electronics and Communication Engineering, SR University, Warangal, India. So, welcome to my channel, Electroverse with Dr. Subhas Das. Please support me with like, share and subscribe. Okay, let's start. So first we will see problem number 1. Okay, here you can see that it is asking that we are going to design a bridge sensor, and that sensor outputs a tiny differential signal of 10 millivolt representing a 1 kg load. So for there we have to see one good point here is that 10 millivolt is that input differential signal, which of course represents 1 kg of load. Now it is asking that you need a 5 volt output, right, which is to be fed to the microcontroller. The two input stage registers are R is equal to 25 kilo ohm, and the output stage registers are matched at Rf by R1 is equal to 2. That means the differential gain of the amplifier is 2. Now it is asking, so the differential gain is 2. Now what value of the external gain setting resistor Rg is required to achieve an output of 5 volt? So here we will see, first we will try to understand what kind of amplifier is this, and then we will try to solve the problem. Okay, so from the mentioned value we can easily understand that this is an instrumentation amplifier. Okay, so as you know the circuit diagram, we can see here that we will be using operational amplifiers, right? Different multi-stage operational amplifiers, where we will connect our input and then we will connect our output through multiple resistors. So here we will be connecting same resistor R here, and this resistor we will be connecting Rg. Then again it will again go with here, of course. Then it will be again one resistor which will be again. So here what we will see that another op-amp we will connect here. Okay, so this will go to here and this will go to our second input. Okay, this will be the output. So these will be the two output ends, and this output we can call this as, let's say, V1 dash, and this as V2 dash. Okay, so now these two will connect with another stage of op-amp amplifier. Okay, so at these two stage we'll call this as R1. We can call this, let's say, R2, and then we can see that, okay, this is another differential amplifier where we have this resistor RAF. Okay, and this is the final output. So this is our total instrumentation amplifier circuit, right? And as you know, the output V out will be equal to 1 plus twice R by Rg multiplied by Rf by R1 and then multiplied by this V2 minus V1. Okay, so now what we can see is that here we need to calculate the value of Rg. Okay, so here we need to see that this value is given, this value is also given, and we need to calculate this value, whereas the gain is given. That means we have the V out and the V in, or in this case it is the V difference is given. Okay, so here in this case we can write that Rf divided by R1 is equal to 2, and we can find the gain from the given values. Okay, then let's see what are the given values. Okay, so now we remember the circuit, so we'll erase this and then we'll try to write all the things. Okay, so here we'll first calculate AV is equal to V out divided by V in is equal to 5 volt divided by 0.01 volt. Okay, so that gives us 500. Why 5 volt? Because you can see it is mentioned that the input voltage is 10 millivolt, which is 0.01 volt, and the output voltage is 5 volt. So ultimately we can see that our differential gain is 500. Okay, now we are going to see that how this AV is suitable for that. So from the previous equation, what we can see is that, okay, so now we can write that AV is equal to 1 plus twice R by Rg into Rf by R1. Okay, so now we will calculate the total value and we will put all the values which is already uh, received from the previous calculation. Okay, let's put all these things. So this will imply that 500 is equal to 1 plus 2 into 25,000 divided by Rg multiplied by 2. Okay, again we can simplify that 250 is equal to 1 plus 50,000 divided by Rg. Okay, again what we can write that 50,000 divided by Rg is equal to 249. Okay, this side we can write again, so that we can see that Rg is equal to 50,000 divided by 249, which gives us the value 200.8 ohm. So this is the answer which was asking about the gain register. Okay, so this is the answer for our problem number 1. Okay, now we'll see problem number 2. Okay, let's read the problem first, then we will try to solve this step by step. Okay, so it is saying that an industrial sensor is connected via a long cable. It picks up 2 volt of 50 Hz hum from the nearby power lines, which in turn is called the common mode noise. Then it is saying that the amplifier has a differential gain of 500, right? Now, if the measured noise at the output of the amplifier is 5 millivolt, okay, what is the CMRR of the output, or sorry, CMRR of the op amp in decibels, right? So the given values are the output voltage and the differential gain. Now, as you know, CMRR stands for common mode rejection ratio. So, the basic purpose of finding this parameter is to understand how good the differential amplifier in rejecting the common modes, because the basic purpose of building any differential amplifier is to enhance the differential gain while rejecting the common mode gain, right? So now, as you know, the formula for CMRR is the ratio between the differential gain and the common mode gain. Okay, let's write these things. So as we can see that this ACM stands for the common mode gain, which we can write that V out, which is of course the noise, and the VCM, which stands for common mode input signal. So here we can see that the output is 500 divided by 2. Okay, so as you can see here, it will give us the value of 0.0025. Okay, now we can write the formula CMRR equals to AD divided by ACM. Okay, so okay, no, so there is this thing is wrong. I wrote the different value. So here the value will be 5, so 0.005, but it was 5 millivolt divided by 2 equals to 0.0025, and this one is 500 divided by 0.0025, which is equals to 200,000. Okay, so now we have to calculate the CMRR. Of course, this is also the CMRR value, but we have to calculate the CMRR in decibel. So how we will do that? So it will be 20 log of this value, okay, which will give us the value nearly is equal to 106 dB. Okay, so this is how we can find the CMRR of that amplifier. Okay, that's it. So let's see the next problem. Okay, so the next problem is saying that while building a function generator, you want to produce a high fidelity sine wave with a peak to peak voltage of 20 volt. So we need to mind this thing, that peak to peak voltage is 24 whereas peak voltage is 10 volt, right? And the frequency is given here as 40 kilohertz. Okay, so what it is asking, it is asking that we have an op amp with a slew rate of 2 volt per microsecond. Now the question is, will the output signal be distorted? What is the minimum slew rate required for this application? Okay, so to answer this question, or to have the proper solution of this problem, we first need to understand the slew rate. Basically, we need to calculate the slew rate from the given values, and then we will compare which this op amp can do or not. Okay, let's calculate the slew rate. Okay, so as we know that the slew rate formula is equal to twice pi f Vp, where f is the frequency and Vp is the peak value. So we can easily write the values here, 2 into the value of pi, which is 3.14 here, and then we'll multiply the frequency, which is 40 kilohertz in this problem. So we'll write this as 40 kilohertz. Okay, and then we'll multiply this by 10, which is the peak value. So you should be mindful that peak to peak voltage should not be put here, because that is 20, but we need to only consider the peak value or the maximum value. So this gives us the value, that is 2513274, and this unit is volt per second. So we can write this 2.51 into 10 to the power 6 volt per second. Okay, or for better understanding, or to have a better comparison with the available op amp with us, what we can do, we can convert this into volt per microsecond. So this will be 2.51 volt per microsecond, right? So now what we can see, that since the op amp's slew rate is 2 volt per microsecond, and for that application we require a slew rate of minimum 2.51 volt per microsecond, so we can see that the available op amp has a lower slew rate than the required 2.51 volt per microsecond slew rate. So the signal will be distorted. So that is the answer, that signal will be distorted. Okay, now let's see the next problem. Okay, so here what we can see here is that the problem is saying that we have a 0.2 volt input signal. Okay, and so this is the input signal, and we have exactly three resistors, 1 kilo ohm, 10 kilo ohm, and 100 kilo ohm. Okay, so we have to build an amplifier by using these resistors. Okay, how we can do that? We can do in many way. We can use simply two resistors, but there are some design conditions. Let's see those things, that we need to produce the output of 2 volt or more from the available input signal. So the available input signal is 0.2 volt, and we need 2 volt or more. That means our gain should be 10 or more. Okay, that is also good, but here is a point we need to consider, that there is some design restriction. that you must use two high value resistors in feedback loop in parallel connection. Okay, so now we can properly design after implementing this condition. Okay, let's see how we can do that. Okay, so for this amplifier we can have two approach, either inverting amplifier or non-inverting amplifier. So why we can go for two? Because there is no phase change, or the phase change is possible or not possible, nothing is clearly mentioned. So we will see that which one is better suitable and maybe which one is not suitable at all. Okay, so as you know, for the inverting amplifier gain is equal to feedback resistor divided by input resistor. Okay, feedback resistor divided by input resistor with a negative sign. Okay, now, and also for the non-inverting case, for the non-inverting amplifier, the gain is little higher, as you can see, 1 plus this ratio, feedback resistor divided by input resistor. Okay, so now we will see what is the feedback resistor here for this case after applying the condition. So it is saying that in the feedback resistor we have to use the two higher values resistor in parallel. So among the three resistors, two higher values are 10k and 100k, right? So when we are making the R equivalent for these two resistors, so R equivalent for these two resistors will be R1 like 10 into 100 divided by 10 plus 100. So that means 1000 divided by 110. Okay, so that will give us the value around 9.09. Okay, so that is the equivalent resistor, this much of kilo ohm of course. Okay, so now as you can see that we have to put two higher value resistors in the feedback loop. So we have only one resistor for the input, so and that is 1 kilo ohm, right? So now if we want to calculate the gain for inverting, okay, so it will be minus 9.09 divided by 1, which will give us minus 9.09. Is there any problem? Yes, there is a problem because your application requirement is to have a gain of 10 or more, because you need to produce a output of 2 voltage or more from an input voltage of 0.2 volt. That means you need a gain of 10 or higher. Which type of amplifier can give that? So from here it is very much clear that we have to implement a non-inverting amplifier. which can give the gain. As you can see that gain for non-inverting amplifier here will be 1 plus this equal to 9.09 divided by 1, which will be 10.09. Is that good? Yes, because as you can see 10.09 is suitable for our application, right? So that means we have to implement a non-inverting amplifier circuit to have this application as well as maintaining the design condition. Okay, so the final circuit will look like this. Okay, okay, forgive me for my drawing, it's very bad. Okay, so here we will connect the input Vi. Here is 1 kilo ohm, here is 10 kilo ohm, here is 100 kilo ohm, and here, sorry, this will be non-inverting, so it will be grounded, and here we will connect the PI. Okay, so this way we will take the P0. So from here we can easily see that P0 is equal to 10.09 of B1 PI. Okay, so this is how we can implement the amplifier which can give the value of the gain 10 or more. Okay, let's say our fifth problem, and that will be our last problem for today. Okay, so the problem is saying that you are designing an inverting amplifier for some specific application, right? Now by mistake your fabrication team did a mistake. Okay, what kind of mistake it did? So it did some component placement mistake basically, and because of that we could see some different kind of output, which is the changing the shape from square to triangular. Okay, let's see what kind of mistake it could happen. Okay, basically we will see the what was the design circuit and what was the fabricated circuit, then we can understand some mistake. Okay. So as per the design, the circuit was supposed to have the inverting amplifier. Okay, so that means, so it was supposed to have inverting amplifier. This Vi, here it should be grounded, this is R1, this is RA, and from here it is supposed to take the PI. So for this case the input and output should have been the similar waveform, only the change should be that. Okay, that change in the amplitude and also the change in the phase. Okay, so this is our expectation, but customer complained that okay, we are not getting this kind of thing. If we give the square wave, we are getting triangular wave. So as you know that this is the typical performance of an integrator by using op-amp. So what kind of mistake the fabrication team might have done is that by mistake they put a capacitor in place of the resistor in the feedback loop, and that circuit would be, if we can see here, is that this circuit would be similarly, if you can just replace a capacitor place of a resistor, this V0, this Vi. Okay, so this is R1 and this is CF. So if they did this mistake that in place of this RF they put some this capacitor CF, then obviously, as you know, V out is equal to this 1 by R1 CF, and this is integral of 0 to T Vi dt plus V0 at 0 point. Okay, so we can see that in these cases, if you give a square wave, you will get some triangular wave. Okay, so this is the most possible mistake they might have did, and that's why the customer received a different shape of the output along with some nominal amplification. Okay, so I hope all of you understood all this solution for these problems, and next video will come up with some different scenario based problem based on the op-amps, of course, and we will also try to solve this. For then, goodbye to all.